In problem number 15, we are asked to approximate the double integral of the function x plus y taken over a square in the xy plane with a Riemann sum with four terms obtained by subdividing the square R, the region of integration, into four smaller squares of equal size, and using the center point of each square as the evaluation point for that square. Let's begin by talking about what this double integral calculates. First, let's look at the function. So the function that we're integrating, the function that is being integrated, is the function z equals to x plus y. And let's think about what the graph of this function looks like. It's a linear equation, and the graph of a linear equation in two variables is a plane in 3 dimensions. Here I graph this plane. And so it is shown in light blue. I'm going to rotate the view so you could get a good idea of what it looks like. So the plane in blue is the graph of the function that we are integrating. Now, the region of integration is the square in the xy plane. The two sides of the square are going along the x-axis and the y-axis, and this length of the side of the square is 4, and so we're integrating our function z equals to x plus y over this square in the xy plane. Now, what this double integral will calculate is the volume of the solid, three-dimensional solid, that is located above the region of integration, above the square in the xy plane, and below the graph of the function z equals to x plus y. So give yourself a few minutes to try to visualize this solid. And if you need to, pause this video and I will then show you what the solid looks like, so you could test whether you were able to visualize this solid correctly. Okay, so let me now show you the solid. So the solid that that this double integral will calculate the volume of looks like this. It's a polyhedron. It's kind of like a pyramid looking, or prism rather, that is built on top of the square in the xy plane, and it is situated exactly between the plane z equals to x plus y and the square in the xy plane. So here's a good view of this solid. The double integral that we are asked to approximate calculates the volume of this object. Now, what about the Riemann sum? So Riemann sum is used to approximate the double integral. We could also use Riemann sums, of course, to approximate regular definite integrals for functions of one variable. And it's a good idea to review that concept before you look at Riemann sums for functions of two variables. The process of making a Riemann sum begins by taking the region of integration and subdividing it into smaller pieces. So let's return to the region of integration. So here I drew the region of integration, so square in the xy plane. The problem is asking us to use a Riemann sum with 4 terms. So that tells us that we need to subdivide the square into 4 smaller pieces. And we will be using pieces of equal size. To achieve this subdivision, we subdivide the sides of our square into 2 equal segments by using midpoints of those sides. And then we draw vertical and a horizontal line through those midpoints. And now you see that our square has been subdivided into 4 smaller squares. Next, for each of these smaller squares, we need to select a point inside the smaller square or in its boundary, which we will use as our evaluation point for that square. The problem instructs us to select the center point of each small square as the evaluation point. So we get 4 points. And of course it's clear from the graph what the coordinates of those points are. So the evaluation points will be 1, 1, 1, 3, 3, 3, and 3, 1. Now, what are we going to do with these points? They're called evaluation points because we're going to evaluate our function at these points. In other words, we will plug in the x and y coordinates of these points into our function. For example, if I'm using the point 1, 1 and calculate the value of our function at that evaluation point, I'm going to get 1 plus 1, that is 2. The value of our function at the evaluation point 1, 3 is 1 plus 3, 4. And you proceed likewise in the exact same way to calculate the value of your function, of our function, at all the evaluation points, and there are of course 4 of them, so we get 4 values, which are 2, 4, 6, and 4. Now, what are these? Now, how are we using these values? So what we're going to do to construct the Riemann sum is we imagine again that this region of integration, it's a square in the xy plane, but imagine the square is sitting inside the 3-dimensional space where we also have a z-axis. This square lies at the 0 level for the z coordinate, and we're going to build prisms, basically a vertical column for each of the 4 smaller squares. On top of each of these smaller squares, we're going to build a column, vertical column, and the values that we obtained here, 2, 4, 6, 4, the values of our function at the evaluation points basically are telling us how tall those columns will be. And so, for example, if you look at the first square, bottom left corner, the column built on top of this square is going to have, will be 2 units tall. The columns built over the next two squares, which are situated diagonally here, they will have height 4. And then the column built on top of the upper right corner will have height 6. And so we'll have these vertical columns. And the Riemann sum with these 4 terms, with these evaluation points, is simply the sum of volumes of those columns. But let's take a look at these columns and how they look. So here's the picture which shows the situation that we have here. The plane is in blue, light blue. That is the graph of our function. The region of integration is in the xy plane. It's a square, 4x4 square. And let me actually zoom in a little bit here so we can get a better view of this 4x4 square. So here it is, and you see that the square has been subdivided into 4 smaller squares, and I also marked the evaluation points, which are the center points of these smaller squares. Now, what we're doing when constructing the Riemann sum is we're building these vertical columns on top of each of these smaller squares. Now the columns will have different height, so you can see that the column built over the left bottom corner is of height 2, and we have 2 columns of height 4 situated diagonally, and then the column in the right upper corner will have height 6. That's the tallest one. And the point of this is that this union of these columns is something that approximates that solid that we are trying to calculate the volume of using the double integral. Okay, I'll return to this picture a little bit later, but now we have everything we need to calculate the Riemann sum. Now, when you have a vertical column like this, a mathematical term for it is a prism. Its volume can be easily calculated by the following formula. Volume of such a prism equals area of the base multiplied by the height of the column times height. This is a formula that you may have seen in high school geometry course. Now here we have 4 small squares. They all are of equal size. Each square is 2 by 2 square, and therefore the area of each of that small square is 4. And so all 4 columns have exact same base area, which is equal to 2 times 2, 4. But the columns have different heights. One column has height 2, one column has height 4, another column has height 6, and then the last one has height 4. So this is how our Riemann sum will look like. I will use RS to represent the Riemann sum. So our Riemann sum with 4 terms with the subdivision of our region of integration into 4 smaller squares of equal size, and using center points of each small square as the evaluation point is going to be 4 times 2 plus 4 times 4 plus 4 times 6 plus 4 times 4. I could have also written this as 4 times 2 plus 4 plus 6 plus 4, factoring out the common area of the base. And so now we can see that this is 4 times 16, and of course that is 64. So the value of this Riemann sum is 64. Now, to conclude this video, let me also show you what happens when we use more and more, when we subdivide the region of integration into more and more rectangles, which of course are going to be getting smaller and smaller. Okay. So I am going to use, see if I can do that here. Yeah, so what I'm going to do is I'm going to actually now increase the number of rectangles that we're subdividing our base square, the region of integration. So here, for example, look at the subdivision that it looks now. Please ignore the evaluation points. I only marked those evaluation points for the original 4 smaller squares, but now we have, as you can see, the original square of integration has been now divided into 12 rectangles, and we can make that subdivision finer and finer, and that's actually a point of constructing Riemann sum. So here's I'm making that subdivision finer and finer by using more and more grid lines, and you can see that now the original square has been subdivided into a whole lot of smaller squares or rectangles, and on top of each small rectangle we build a vertical column with the height determined by the value of our function at one of the evaluation points. So here's how this picture now looks. And let me zoom out. And you can now see that the collection of all these vertical columns is approximating the solid, right? The solid whose volume our double integral calculates. Let me remind you, so this solid right here. The union of green vertical columns now looks almost like really close to the solid whose volume we're calculating. So the point I'm trying to make here is that when we increase the number of subdivision rectangles, and each rectangle in the subdivision becomes smaller and smaller, the union of vertical columns will be getting closer and closer to the solid whose volume the double integral calculates. And the Riemann sum, which is the sum of volumes of those vertical columns, will be getting closer and closer to the value of the double integral, which is the volume of the solid.